The paper that will be the final paper of the morning session is by C.W. Carlson, entitled Rocket Observations of Auroral Substorm Electric Fields and Electron Fluxes.
In this talk, I'll be presenting some data obtained from 2 rocket flights flown during auroral substorms from Churchill. The one flight, I'll just discuss one result for the electric field. The 3 main things I'd like to bring up in this talk are the electric fields observed in relation to the auroral precipitation pattern, anisotropy of low-energy electron fluxes, they'd be field-aligned fluxes, and then finally the energy spectra of the electrons and how they relate to other regions in the magnetosphere. This is data from the first flight, and on this rocket there were 2 independent techniques for measuring the electric field. There were 2 barium releases, and in addition there were double probe electric field detectors. This was during a strong substorm. It was 1000 gamma Bay, and in this sequence of all-sky camera pictures you see the first barium release, and you can see it's moving quite rapidly southward. The electric field during this time was very strong, and you can see it's also widespread precipitation all over the sky. When the barium cloud got into the darker area, lower precipitation region, the field decreased by about a factor of 2. And this is a positive correlation between the field magnitude and the precipitation pattern. And this during a substorm magnetic bay. Okay, this is the only results I'm going to show from that flight. The remaining results will be from another rocket flown during a slightly weaker bay. This is a substorm, had about a 400 gamma Bay maximum, and the rocket was flown shortly after the arcs had moved northward of the overhead at Churchill, and also the Bay magnitude was recovering somewhat. During most of the flight, the magnetometer saw about 100 gamma. Again, there were 2 separate techniques for measuring the electric field. There was a double probe electric field measurement, and in addition there was a differential ion flow measurement. And these are the electric field corresponding to the ion flow. Just comparing the 2 results, and you can see the general agreement is pretty much 1-to-1. The second point in this graph is the highly structured field that you see during the first half of the flight, and then the very quiet field you see during the second half. Later in the talk I'll point out that this corresponds to what we can say is the auroral, or the polar cap boundary. The region northward, the rocket trajectory was generally in a poleward direction, so this corresponds to the northward region. This is down in the heavy precipitation and the arc region. Okay, then if we include the particle measurements together with the electric field, again we see that the highly structured field corresponds to the region of high precipitation. This is 30 to 100 kilovolt, 15 to 30 kilovolt, 5 to 15 kilovolt, half kilovolt to 5 kilovolt, and then finally there's essentially a total flux measurement above 5 eV. A couple of features that show up here are near the beginning of the flight, the spectrum is very hard. There are quite intense fluxes all the way up to the 30 keV detector. We go sort of through 2 very strong precipitation regions, and then further northward the spectrum gets much softer. You can see the total flux is essentially the same upper level at all of these intense regions, but the spectrum is considerably softer near the end. The other point is that the electric field has very sharp boundaries that coincide with sharp boundaries in the precipitation pattern. You can see it at this region. It's as high as 100 millivolts per meter along this sharp boundary. Again, in this region, there's a very intense electric field corresponding to the region of high precipitation. Again, these are the sharp field boundaries, and the high field magnitudes correspond to the regions where it's a relatively hard spectrum. You can see where the spectrum is softer, the electric field is very close to zero, much weaker than in the stronger precipitation regions. Oh yeah, there's another point in here. This corresponds to a visible arc that I'll show in a moment. You can see in the electric field, apart from this very sharp boundary and strong field, the field is generally fluctuating through this region, so that you have sort of both cases, a very strong electric field corresponding with the boundary, and then a fluctuating field later. Now if we compare this with the all-sky camera picture and the trajectory of the rocket, you get the following pattern, that there's a very strong equatorward field. If you consider the coordinate system of the arc, the field is directed equatorward inside of the high precipitation region. The all-sky camera pictures are used only in a general sense to compare with the particle precipitation we saw. So it's a little hard to map from the camera pictures exactly the visible regions. But this general pattern is in good agreement with what the camera sees. Also, the fluctuating region in the particles and the electric field is in this folded part of the arc, and it was very turbulent structure there. Then northward of the bright arc, there is this region of soft electrons, and then at this point, it probably corresponds to the polar cap boundary. Northward of that, there's the general anti-solar convection flow of the plasma. If you consider the flow through this whole picture, there's a sort of a dead region here where the flow is very weak. In the arcs, there's a very strong flow, and also would likely be a contribution to the electrojet, since you have a strong southward field, hard electron precipitation, which will increase the conductivity along this strip. Then in this region, there's again a shear in the flow. Here it's generally eastward along the arc. Reverses has pretty much of a westward flow through here. And again, in this portion of the first crossing of the arc, you see the general electrojet direction of the flow with a strong shear at the boundary. Okay, this fits nicely to sort of a simple-minded model of what you can have with hot electrons coming in, enhancing the Hall conductivity, setting up a polarization field if the field line currents don't close completely. This would be a parallel flow of hot electrons. You might think of another return flow southward of the arc to close this current system, and then an electrojet associated with the polarization field and enhanced conductivity. Okay, in that connection we had low energy particle detectors, which were oriented along up and down the rocket axis. This is 0 to 60 electron volts, and the plotted here is the differential flux between the two detectors. You can see the flux crossed over at about 25 eV, so there's a net flux into the ionosphere here, net flux out of the ionosphere at this point. There were actually two redundant detectors, one that was sweeping that you saw in the previous slide, and then there's a total particle flux detector. And then the electric field and hot particle data are shown as a reference here. This is the total flux measurement, and there's a region, if you remember the arc orientation, this region corresponds to an equatorward side of the arc boundary. This data should be ignored. It's due to discharge in the detector. However, the circles, which are the swept analyzer, and the continuous lines, which are the difference between the two total flux detectors, show very good agreement in this region where there's a net flux into the ionosphere. Southward of the arc, and sort of between the fold and the other crossing of the arc, we see a net outflow of these superthermal electrons. I guess I have to end at that point.
Any discussion?
The variation of spectrum hard to soft is essentially spatial. What you are saying is.
Yeah, maybe I can go to that last slide that I skipped over. There it is. This shows the energy spectra at different times in the flight. Early in the flight, the spectrum is quite hard. That's this curve here. And it's very similar to what the Vela hot plasma sheet average spectrum would be. So that it's quite hot, but not a terribly intense spectrum. Inside the arc, it's much more like the ski jump spectrum, or whatever you want to call it. A very large sort of back porch on the spectrum here between 10 and 30 keV. And this is seen pretty much all through the visible arc part of the spectrum. Then northward of that, it's much softer and looks maybe more like a quiet arc spectrum, a small peak down at about a kilovolt.